Greetings, cosmic enthusiasts. Get ready to embark on a celestial voyage as we delve into the depths of our solar system. My name is Annabelle, and today I will be your host. Our focus is on the enigmatic and captivating eighth planet from the Sun, Neptune. Neptune is the eighth planet in the solar system, the last from the Sun since the reclassification of Pluto to the category of dwarf planet in 2006. Belonging to the group of gas giants, it is slightly smaller in size than Uranus, but has greater mass, equivalent to 17 Earth masses. Neptune orbits the Sun at an average distance of 30.1 astronomical units. The planet is formed by a small rocky core around which there is a layer possibly made up of water, ammonia, and methane, on which lies its turbulent atmosphere, made up predominantly of hydrogen and helium. In fact, notable weather events occur on Neptune, including the formation of several layers of clouds, visible cyclonic storms, such as the now extinct Great Dark Spot, in addition to the fastest winds in the solar system, which reach more than 2,000 km/h. The solar radiation received by Neptune would not be enough to provide such energy to the turbulent atmosphere, so it was discovered that the heat radiated from the center of the planet plays an important role in maintaining these extreme meteorological events. The small amount of methane in the upper layers of the atmosphere is, in part, responsible for the planet's blue color. 14 known natural satellites orbit around Neptune, of which Triton stands out, by far the largest. A tenuous and unusual ring system also exists, exhibiting an irregular structure with concentrations of material that form arcs. Its gravitational influence affects the orbits of smaller bodies located beyond, in the Kuiper belt, entering into orbital resonance. Seen from Earth, Neptune has a high magnitude. The brighter the star, the smaller its magnitude, making it impossible to observe with the naked eye. Its existence was suspected only after careful observation of Uranus's orbit, which showed slight irregularities due to Neptune's gravitational perturbation. After mathematical analysis with conclusions obtained independently by John Couch Adams and Urbain Le Verrier, they obtained the approximate positions of where the planet should be on the celestial sphere. After several searches with the aid of telescopes, on September 23, 1846, they found the planet, whose name was later chosen to honor the Roman god of the seas. To date, the only space probe that has visited the planet was Voyager 2 in 1989, whose passage allowed unprecedented photographs and information to be obtained, still being the main source of data on what is currently known about the planet. The planet furthest from the Sun belongs to the group of gas giants, being the fourth largest in the solar system, but its mass is greater than that of Uranus. Its radius is equivalent to 3.91 Earth radii, about 24,000 kilometers, while its mass corresponds to 1714 Earth masses. Although it is in the group of gas giants, Neptune as well as Uranus are much denser and less massive than Jupiter and Saturn. However, its size is still much larger than the dimensions of telluric planets. Due to its rapid rotation, about 16 hours and 7 minutes, the planet has a slight oblateness. Therefore, the equatorial radius, 24,764 km, is greater than the polar radius, 24,340 km. The acceleration due to gravity on the planet is 1115 ms2, slightly greater than that of Earth, and the escape velocity is 23.5 kms. Along with Uranus, Neptune belongs to the class of gas giants, as it has a large mass of volatile compounds that are found in the form of ice in the distant regions of the solar system. Furthermore, the models that described the internal composition of the two planets are quite similar to each other. While in the two largest gas giants, Jupiter and Saturn, hydrogen and helium make up the majority of the planet's mass, on Neptune these elements are abundant only in the atmosphere, whose estimated thickness is 5,000 kilometers. Although it has slightly smaller dimensions, Neptune has a greater mass than Uranus, due to the fact that Neptune's specific mass is 0.64 GCM3 compared to Uranus's 0.3 GCM3. It is inferred from the density of the planet, not so light to be composed of light gases, nor so heavy to be composed of silicates and metals, that it is predominantly formed by water, methane, and ammonia. Although these substances are known as ices, they are not necessarily in a solid state inside the planet. These compounds are possibly more compressed inside the planet, which increases their density, which could also be caused by the greater content of rocky compounds in their internal layers. Neptune probably has a core of rocky material with a mass similar to that of Earth, whose temperature must be higher than 5100 degrees C, possibly higher than the core of Uranus. Around it, there would be a large ocean, a layer formed mainly by oxygen, nitrogen, carbon, and hydrogen, kept under great pressure and temperature. However, the term does not imply that there is necessarily a liquid layer on the planet, but in fact a region where these elements can be found in isolated atoms or forming chemical substances, mainly water, methane, and ammonia. However, the proportion of these elements in the constitution of the planet is not known. A higher amount of hydrogen could imply its manifestation with metallic characteristics, which would allow the flow of electric current and influence the magnetic field. Chemical reactions can also occur between chemical elements and substances, which would have as products, for example, molecular hydrogen, which would rise to the atmosphere, and diamond, which would sink towards the nucleus. Neptune's thermal flux has a factor of 2.6. That is, the planet emits 2.6 times more thermal energy than it receives from the sun. Therefore, the convective activity of the atmosphere is influenced by energy coming from the interior of the planet, being decisive in explaining the great variability of observed meteorological events. On terrestrial planets, the core's heat source comes from radioactive decay, while on Jupiter, thermal energy comes from the condensation and internal movement of helium gas. However, radioactive elements are not very abundant in the confines of the solar system, and the amount of helium in the planet's total composition is not very significant. Therefore, there is currently no explanation for the origin of the planet's additional internal energy. A process of planetary differentiation in Neptune's mantle layers could contribute to the release of thermal energy. Neptune's atmosphere is in many ways similar to that of Uranus. However, its dynamics present itself in a complex configuration of strong winds that sweep the planet, in addition to the formation of cyclonic storms and clouds, with clearly visible visual characteristics. Like the other giant planets, Neptune does not have a visible defined surface, which is why altitudes in the atmosphere are measured from a reference point whose pressure is 1 bar. From this reference level, the atmosphere extends to a depth of 5,000 kilometers, where the pressure reaches 100,000 bars. Neptune's upper atmosphere is made up of 79% hydrogen, around 18% helium, and the remaining majority of methane, the presence of which gives the planet its indigo blue color by absorbing incident red radiation. It is assumed that some other component of Neptune's atmosphere contributes to its accentuated color, since Uranus has a similar amount of methane in its atmosphere, but has a lighter color. This observed layer represents only a small fraction of the planet, corresponding to about 15% of the planet's radius. The temperature of the Neptunian atmosphere varies depending on altitude. At an altitude whose pressure is equivalent to 0.1 bar, the temperature reaches a minimum of 50 K, 223 degrees C, and rises as the pressure decreases, that is, as the altitude increases, reaching up to 327 degrees C at a pressure of hundreds of billionths of a bar, which is equivalent to an altitude of 2,200 kilometers above the reference level of 1 bar. Below the pressure level of 0.1 bar, the temperature increases as the pressure increases. At the reference level of 1 bar, the average temperature is 74 K, 199 to 15 degrees C. The high temperature of the upper layer of the atmosphere, although common on all other giant planets, still remains a mystery, as it cannot be caused by solar ultraviolet radiation due to the great distance to the sun. It is possibly related to the behavior of the Earth's magnetic field. Based on temperatures, the atmosphere can be divided into layers. From the deepest part of the atmosphere to the level where the lowest temperatures occur, where the pressure is 0.1 bar, is the troposphere, where fog and clouds normally occur. Bounded by the tropopause, the next layer is the stratosphere, in which the temperature increases with altitude up to the mesosphere. Above this is the thermosphere, where the pressure is on the order of 10 microbars and high temperatures occur, followed by the exosphere, which is extremely rarefied. Methane, although not so abundant, interferes with the dynamics of the Neptunian atmosphere. When hit by the sun's ultraviolet rays, methane molecules break down through photolysis and form hydrocarbons and polymers, such as ethane and acetylene, which form a mist. This haze sits above the methane cloud layers. These particles fall to the depths of the atmosphere, where the temperature and pressure are higher, where the abundance of hydrogen once again promotes the formation of methane, which, through convective currents, returns to the upper layers of the atmosphere, thus establishing a cycle in which the proportion of methane in the atmosphere remains constant. However, the amount of methane in the stratosphere is abnormally high, contrary to what theoretical models predict. Methane molecules would theoretically be taken to the high layers by strong convective currents. It turned out, however, that the planet's south polar region is 10 degrees C warmer than the planet's average temperature. In this way, methane would find favorable conditions to escape to high layers of the atmosphere, spreading throughout the stratosphere. This temperature is related to the southern hemisphere summer. It is expected that when summer arrives in the northern hemisphere, the same will occur in the opposite polar region. The planet is swept by strong winds that form belts, similar to other gas giants. These large bands run parallel to the planet's equator and follow at low latitudes in a retrograde direction opposite to the planet's rotation. As latitude increases from the equator, they gradually reverse their direction until they become prograde in the direction of the planet's rotation. Above latitude 70° north and south, convective currents are likely ascending in mid-latitudes and descending near the equator and at the poles, fueled by internal energy radiated from the planet's core. Observations made over decades by the Voyager spacecraft, the Hubble Space Telescope, and other telescopes on Earth have revealed long-term changes that have been occurring in the planet's atmosphere. In particular, an increase in atmospheric activity was noted in the southern hemisphere until 2003, when cloud formation reached its maximum. The planet's stratosphere has also shown a gradual increase in temperature, for unknown causes. Due to the inclination of its axis of rotation at just over 28 degrees, Neptune has seasons that last approximately 40 years, despite the intensity of the sunlight that reaches the planet being 900 times less than that on our planet. The formation of clouds in the southern hemisphere of the planet would be associated with the arrival of summer, when incident solar radiation is at its maximum. The intensity of storms also appears to be linked to the gradual change of season. The planet has also shown a slight increase in brightness over the last 2 decades due to greater cloud formation, which may also be related to the change of season and greater insolation in the southern hemisphere. Greater warming, especially at high latitudes, causes convective currents that carry methane to the upper layers of the atmosphere, where crystals that form clouds are formed. There is also evidence that the solar activity cycle, which repeats every 11 years, could also influence the greater or lesser amount of clouds periodically. Neptune's atmospheric dynamics are marked by a variety of rapidly evolving cloud types that interfere with the planet's appearance and thermal flow. The planet has wind circulation bands just like Jupiter or Saturn. However, they are practically indistinguishable visually. In observations at infrared wavelengths, however, it is possible to observe the existence of thick bands extending over tens of degrees of latitude and involving the entire planet, in addition to showing great variation in width over a few years. Contrasting with the blue color of the planet, clouds of white methane crystals appear, analogous to the cirrus clouds formed by water crystals on Earth. They generally have a short period of existence, forming and dissipating in a matter of hours. They are located above the pressure level of 1 bar, above the other cloud levels over which they cast shadow. Clouds of this type are commonly associated with cyclonic storms, as occurred in conjunction with the Great Dark Spot, possibly at a pressure level of 0.1 bar. These clouds are easily identifiable when observed in infrared, as they reflect much of the radiation incident in this wavelength. Theoretical models of Neptune's atmosphere predict the location of other cloud layers in the inner layers of the planet's atmosphere, below the layers observed by Voyager 2. They should be formed by hydrogen sulfide and ammonia between 2 and 5 bar and water, and hydrosulfide crystals of ammonium between 20 and 50 bar. Only 2 cloud layers were directly observed, the upper one being formed by methane, and the lower one being a thick and opaque layer, possibly the top of the hydrogen sulfide cloud layer. The visit by the Voyager 2 probe revealed that, even despite being extremely far from the Sun, Neptune has turbulent atmospheric dynamics, with strong winds and cyclonic formations that evolve quickly. They present visually distinct structures unlike Uranus. The average speed of the winds that circulate the planet in a direction contrary to the rotation movement at the equator is around 400 meters per second, and at the poles in a prograde direction around 250 ms, already much higher than the wind speeds at the Earth. However, the highest speeds recorded on the planet reach more than 2,000 kilometers per hour, being the fastest recorded in the entire solar system. This dynamic is mainly caused by internal energy radiated from the center of the planet, producing convective currents. One of the most notable storms recorded was the Great Dark Spot, photographed by Voyager 2 as it passed the planet. Comparable to Jupiter's Great Red Spot, the spot was located 30 degrees south of the equator. It was an anticyclonic storm 12,000 by 18,000 kilometers long, which decreased to 5,000 by 7,600 kilometers after 8 days of observation by Voyager 2. Observations carried out a few years later with the Hubble Space Telescope showed that the great spot darkness had completely disappeared, leaving no trace. Cyclonic storms on the planet appear to form holes in the upper cloud layers, revealing the lower layers. However, in 1994, Hubble made it possible to observe a new large storm in the other hemisphere, similar to that observed by Voyager 2, dubbed the Great Northern Dark Spot, which lasted for 2 years. Voyager's photographs also showed a set of white clouds close to the Great Dark Spot region, but which circled the planet faster, which is why they were nicknamed Scooter. To the south of the large spot there was another storm of smaller dimensions, called Little Dark Spot. Neptune, as discovered from data sent by Voyager 2, has a magnetic field whose main dipoles are inclined 47 degrees in relation to its axis of rotation, in addition to its center being displaced from the center of the planet, with a distance greater than half the radius of the planet. For this reason, the magnetic poles are found at low latitudes on the planet, in addition to being more intense in the southern hemisphere, towards which it is displaced. The magnetic field intensity at the atmospheric level of 1 bar varies between 1 and 0.1 Gauss between the southern and northern hemispheres respectively. Its origin is possibly the current of ionized fluids inside it, creating a dynamo effect similar to that of Earth and Uranus. The distribution of the Neptunian magnetic field, however, presents a complex configuration in which there is a superposition of a quadrupole field, which produces 4 magnetic poles equally spaced between each other, and an octopole whose intensity sometimes exceeds the dipole, the most intense case being of this fact throughout the solar system. Neptune's magnetosphere, the region free from the effects of the solar wind created by the planet's magnetic field, extends from the shock arc, the region where solar wind particles are decelerated by the magnetic field, located about 39 radii from the planet in front of you, to the magnetopause, 26 radii from the planet in the opposite direction. The configuration of Neptune's magnetosphere varies according to the rotation of the planet and the magnetic field, ranging from a normal configuration similar to the Earth's magnetic field to one in which the magnetic pole points directly in the direction of the solar wind, whose cycles are repeated with each rotation of the planet. This causes the heating of the upper layers of the atmosphere, as well as the irregular emission of electromagnetic radiation at radio wavelengths. In fact, Neptune's magnetosphere has the lowest density of protons and electrons compared to other gas giants. The tenuous atmosphere of Triton, its largest natural satellite, supplies nitrogen ions to the magnetosphere. However, the constant disorientation of the Neptunian magnetosphere causes particles trapped in it to pass through the planet's satellites and rings, which end up absorbing them. Weak auroral emissions have been detected on Neptune, possibly originating near the magnetic poles. Neptune completes a rotation around the Sun every 164.79 Earth years, orbiting at a speed of approximately 5.45 kilometers per second. From the point where it was discovered, Neptune completed its first orbit only in July 2011. The semi-major axis of the planet's orbit, the average distance between it and the Sun, measures approximately 30 astronomical units, which is equivalent to 4.49 billion of kilometers. Neptune's orbit has an eccentricity of only 0.011, which makes it one of the most circular among the planets in the solar system. The first attempts to accurately obtain Neptune's rotation period were made using spectroscopy and photometry techniques, which left considerable uncertainty in the measurements. Spectroscopy made it possible to obtain the speeds at which the two limbs moved in relation to the Earth, and knowing the diameter, the rotation period was obtained. The photometry sought to observe the variation in brightness caused by the visibility of a large structure on Neptune, measuring the interval between them. Only in 1979 did telescopes reach sufficient size to distinguish bright regions, the clouds, from which a rotation period of around 17 hours was obtained. However, in addition to the inaccuracy of the equipment used, these instruments only obtained the speed of the planet's atmosphere. The winds rotate at different speeds depending on the planet's circulation bands. Furthermore, like other gas giants, the planet presents differential rotation. It was only after the visit of Voyager 2 that the rotation period of the planet's center was established with reasonable precision, being 16 hours and 7 minutes. Neptune's axis of rotation is tilted at 28.3 degrees, similar to the tilt of the Earth's axis, which is 23.5 degrees. Therefore, the planet presents seasonal variations in the solar radiation received in the northern and southern hemispheres, just like Earth. Although on Neptune each season lasts approximately 41 years, Neptune's gravitational influence plays an important role in the orbital movement of objects that lie beyond its orbit. In the Kuiper belt, populated by large icy bodies and dwarf planets. Some of these objects enter orbits resonant with the planet's orbit, which generally makes the orbit stable, avoiding the body's encounter with Neptune, which would strongly deviate their trajectory. The dwarf planet Pluto is in 2-3 resonance with Neptune. That is, while Neptune completes 2 revolutions around the Sun, Pluto completes exactly 3. Thus, even though Pluto's orbit comes closer to the Sun than Neptune's at a certain point, the two bodies never come closer. For common resonance values, names are given to groups of bodies with this behavior. Bodies that are in a 2-3 resonance are collectively called Plutinos, while those that are in a 1-2 resonance are Tutinos. Neptune's orbit is shared with Trojan objects, which are distributed close to points located 60 degrees in front and behind the planet, at Lagrange points L4 and L5 respectively. In January 2016, only 12 Trojans were discovered in Neptune's orbit, 9 of which were located in front of the planet. The first to be discovered was in 2001 QR322, during the Deep Ecliptic Survey program in search of smaller bodies. The population of Neptunian Trojans, however, must be much larger, possibly comparable to the number of Jupiter Trojans or even greater. This is because Lagrange points are gravitationally stable, just like in Jupiter's orbit. Only one quasi-satellite of the planet Neptune has been discovered to date, the asteroid 309239 2007 RW10. Seen from Neptune, this 250-kilometer diameter object appears to orbit around it. Although it orbits the Sun, it is in 1-1 resonance with the planet, although it should remain in this configuration for only the next 12,500 years. O planeta Netuno se formó a partir da acreção de parte da matéria do disco protoplanetário existente ao redor do Sol primordial, inicialmente pela fusão de diversos planetesimais, de acordo com a hipótese nebular. Posteriormente, o núcleo de rocha o gelo que se formara adquiriu dimensões suficientes para atrair o gás e a matéria ao seu redor até que o disco desaparecer por completo. Esse processo teria durado somente 10.000 milhões de anos. Após cessar a absorção de gases, muitos planetesimais que não foram incorporados aos planetas gigantes ficaram entre suas órbitas. Modelos numéricos sugerem que Netuno teria se formado bem mais próximo do Sol, somente a 23 UA. Contudo, a interação gravitacional dos gigantes gelados como os planetesimais os jogava para o interior do sistema solar, causando o período caótico do intenso bombardeio tardio. E, por conservação de energia, impulsionava Urano e Netuno para mais longe do Sol. A migração planetária pela qual o planeta passou teve reflexo na configuração do cinturão de Kuiper, arrastando alguns objetos para órbitas ressonantes, nas quais se mantém até o presente momento, direcionando-os para fora de sua órbita. Tritão provavelmente não se formou próximo a Netuno, mas teria sido capturado pela gravidade do planeta em algum momento em sua história, por isso possui uma órbita retrograda. Sua aproximação ao planeta teria perturbado a órbita de eventuais satélites pré-existentes, levando a colisão entre eles. A configuração natural da órbita de Tritão faz com que o mesmo se aproxime gradualmente do planeta até que, em algum momento no futuro, o satélite atinja o limite de Roche e a gravidade de Netuno o faça se romper completamente, formando-se então grande sistema de anéis. Neptune is surrounded by a faint system of rings, the existence of which had been suspected since the 1980s, and which were confirmed by the Voyager 2 probe. A reduction in the brightness of the stars in the vicinity of the planet was observed during an occultation, but never symmetrically. Voyager 2's photographs showed that they were actually rings with little material in them, much of it concentrated in agglomerations that form arcs, brighter in comparison to the rest of the ring itself, a unique feature in the solar system. The rings are mostly made up of dark dust particles that reflect little sunlight, possibly formed by methane ice. The arcs formed in one of the rings could be created by the recent defragmentation of a small satellite a few thousand years ago. The entire ring system is suspected to be relatively young, having been formed less than 1 million years ago. The ring system, according to continuous observations, appears unstable because some of the arcs are becoming more rarefied and disappearing. Neptune has 14 known natural satellites. The largest of them is Triton, who has many peculiar characteristics. One of them is that the satellite circles Neptune in a retrograde orbit, that is, in the opposite direction to the planet's rotation, being the only one of the large satellites in the solar system to perform such a movement, which could be explained if the satellite had not moved. Triton is approximately 2,700 kilometers in diameter, being more than 6 times larger than Proteus, the second largest moon on the planet, which is 420 kilometers in diameter. Its surface is formed by layers of frozen nitrogen, methane, and carbon dioxide, marked by features that suggest geological activity. Triton also has a rarefied and practically transparent atmosphere, composed mainly of nitrogen. The satellite has one of the lowest temperatures ever detected in the solar system, reaching just 35 K to 238 degrees C. Nereid, which together with Triton and Larissa, were the only known satellites of Neptune until the Voyager 2 flyby, has an extremely elliptical orbit and a diameter of only 340 km. In addition to its small size, it has low reflectivity, which makes it extremely difficult to observe from Earth. It is the third largest natural satellite in the Neptunian system, preceded by Proteus, whose diameter is 420 km. In addition to Proteus, 5 other natural satellites were discovered from images from Voyager 2, including Naiad, Thalassa, Despina, and Galatea, and the rest from large telescopes on Earth. The peculiar configuration of Neptune's satellite and ring system suggests a troubled history. In particular, Neptune's gravitational capture of Triton may be the cause of Nereid's unusual orbit, as well as being responsible for clearing the vicinity of its orbit around the planet. Furthermore, the existence of many small moons in the vicinity of the rings could be the source of dust that maintains the rings through small impacts that happen with comets or meteors. Due to its immense distance from Earth, Neptune cannot be observed with the naked eye, as it has a magnitude that varies from approximately plus 7.8 to plus 8, while on a dark night the faintest observable stars have a magnitude of plus 6. Therefore, its observation can only be done with the help of a telescope. Triton shines with a magnitude of only 13.4, requiring at least a 200mm telescope to observe it. The visible disk of the planet Neptune has an angular diameter that varies between 2.2 and 2.4 arcseconds, which is why its observation is strongly disturbed by atmospheric turbulence. The synodic period, in which the planet returns to the same longitude on the celestial sphere from Earth, is 367.5 days. Neptune's albedo is 0.29, meaning the planet reflects almost a third of the light it receives from the Sun. Galileo's astronomical drawings show that he observed Neptune on December 28, 1612, and again on January 27, 1613. On both occasions, the planet was very close, in conjunction to Jupiter. But as he thought it was a fixed star, he cannot be credited with the discovery. During the period of its first observation in December 1612, Neptune's apparent movement was exceptionally slow, as on the same day the planet had begun the retrograde period of its apparent movement in the sky, which could not be perceived from Earth through of Galileo's primitive instruments. After the discovery of Uranus in 1781, its orbit began to be established in detail based on numerous observations, made mainly by the French astronomer Jean-Baptiste Joseph Delambre. However, the observed position of the planet did not agree with established calculations. That is, it did not occupy exactly the position predicted by mathematical models, being a little behind or a little ahead in its orbit. It was then suggested that these gravitational disturbances would be caused by another celestial body that would orbit the Sun in addition to Uranus. In this way, from careful observations of variations in the position of Uranus, it would be possible to calculate the position of the unknown body. The challenge was accepted by John Couch Adams, an astronomer at the University of Cambridge in 1843, when he began to work with the data obtained until then, proving mathematically that it was possible for the existence of another celestial body that would be responsible for the perturbation of Uranus's orbit. He sent the results to George Biddle Airy, the British astronomer royal, who did nothing with the results sent by Adams until 1846, when another French astronomer, Urbain Le Verrier, published results of his independent calculations of the location of the new planet, similar to the position obtained by Adams. Airy then assigned 2 astronomers, James Challis and William Lassell, to search for the planet. On 2 occasions, Challis claimed to have seen the planet, but his observations needed to be confirmed. His strategy for finding the planet consisted of observing a certain region of the sky and comparing it with star charts. An observed star that was not on the chart could possibly be the planet. Meanwhile, Le Verrier, by letter, persuaded astronomer Johann Gottfried Galle of the Berlin Observatory to search with the site's refracting telescope. Heinrich Louis d'Arrest, a student, suggested to Galle that they compare a chart of the sky recently drawn in the region of Le Verrier's predicted location with the currently observed sky to look for the planet's characteristic shift. The following night they observed its slight change in position, which confirmed that it was indeed a planet, which was 1 degree from where Leverrier had predicted it would be, and about 12 dig from Adams's prediction. Challis later realized that he had observed the planet twice in August, but had not identified it due to his casual approach to the work. At the time of the discovery, there was much rivalry between the French and British over which country deserved credit for the discovery. An international consensus was later reached that Leverrier and Adams deserved joint credit. However, the issue is now being re-evaluated by historians due to the rediscovery in 1998 of the Neptune papers, historical documents from the Greenwich Observatory, which were apparently stolen by astronomer Olin J. Egan and hidden for nearly 3 decades without being rediscovered in his possession until immediately after his death. After reviewing the documents, some historians now suggest that Adams does not deserve credit equally with Leverrier. In a 1992 article in his newspaper Dio, he considers the British claim a robbery. Adams did some calculations, but he was somewhat uncertain about where he said Neptune was, says Nicholas Collerstrom of University College London in 2003. Shortly after its discovery, Neptune was simply called the planet outside Uranus. Gall was the first to suggest a name, proposing to name it in honor of the god Janus, claiming the right to name his discovery. Leverrier quickly proposed the name Neptune for his new planet, falsely claiming that the name had already been officially approved by the French Bureau des Longitudes. In October, he even named the planet Leverrier after himself, and was loyally supported by the director of the Paris Observatory, François Arago. However, as this suggestion met with stiff opposition outside of France, French almanacs quickly reintroduced the name Herschel for Uranus in honor of its discoverer, Sir William Herschel, and Leverrier for the new planet. On December 29, 1846, Friedrich Georg Wilhelm Struve publicly declared himself in favor of the name Neptune for the Russian Academy of Sciences, and within a few years Neptune became the internationally accepted name. On October 10, 1846, 17 days after the discovery of Neptune, English astronomer William Lassell discovered its main satellite, Triton, at the request of John Herschel, who had written him a letter 9 days earlier. At the end of the 19th century, the hypothesis was created that irregularities observed in the movement of Uranus and Neptune were caused by the presence of another, more outer planet. After extensive search campaigns, Pluto was discovered on February 18, 1930, at the coordinates predicted by the calculations of William Henry Pickering and Percival Lowell. However, the new planet was too distant to generate the observed irregularity in Uranus's motion, while the irregularity in Neptune's motion was actually an error in calculating the planet's mass, which was defined with the Voyager mission. The discovery of Pluto was therefore somewhat accidental. Due to its great distance, little was known about Neptune, at least until the middle of the 20th century, when Gerard Kuiper discovered its second moon, Nereid. The largest amount of data obtained about the planet was collected from the only probe that has ever passed close to Neptune, Voyager 2. Launched in 1977, the probe was initially scheduled to visit Jupiter and Saturn, but took advantage of the favorable position to visit the 2 other giants, Uranus and Neptune, in a single trip, using the assisted gravity technique, in which the gravitational attraction of one planet is used to direct the probe to the next. Voyager 2 made its closest approach between August 24th and 25th, 1989, when it passed less than 5,000 kilometers above the planet's atmosphere, although observations took place between June and October of the same year. A few hours later, it passed within 40,000 kilometers of Triton, gathering high-resolution images of its surface. The proximity allowed the probe to collect detailed data on dimensions, composition, and magnetic field, in addition to discovering the ring system and 6 new natural satellites, and monitoring their complex atmospheric dynamics through around 10,000 photographs sent, in addition to other data. Officially, there are no missions planned for the planet Neptune, although many proposals have been made, including the Neptune-Triton orbiter. However, observation of the planet remained continuous, using the Hubble Space Telescope and large telescopes spread around the world. These observations make it possible to monitor the dynamics of the emergence of clouds and storms in the planet's atmosphere, using equipment that allows data to be collected at various wavelengths. However, the level of detail is much lower than the richness of detail provided by the probe. In conclusion, Neptune stands as a testament to the awe-inspiring diversity within our solar system. But before we wrap up, don't forget to hit that subscribe button, giving you a front row seat to our future cosmic adventures.